attempt quiz, follow the device study plan. Please try to attempt all the quizzes. Right. Now, I think we have solved all the questions, but that is the question. So before that, what is the high frequency analysis? I will explain, but what is the answer for this question, everyone? A MOS capacitor made using P-type substrate is in accumulation mode. The dominant charge in the channel is due to the presence of. What is the answer? Very, very simple. In accumulation mode. P-type substrate means always remember it talking about the body. Body is the P-type. This is N-channel MOSFET. Here we are giving high negative voltage. 94% students have given the answer and 1 student have given the C option. No problem. Sujoy Mandal, Vignesh, Navneet, Ronita Roy, Jagdish and Mohan. Oh, Priya Mohan. Sibu Bhatt. Right. Sibu, Ravi, Reza. Everyone. Pankaj, what is your doubt? What is your doubt? Pankaj, you are asking about the pole and you are giving the answer C. Positively charged ions means what? This is called ions. This is not a donor ions. We are having accumulation means accumulation of the holes here. Right? This is the accumulation of holes when we are giving a negative charge. There is the accumulation of holes. Okay. Then this is the A is the option. Second, now this is the high frequency. So one student asked that what is the frequency? That is the frequency effect. Now, first of all, high frequency means what? When I am talking about the high frequency response, always remember we are giving two types of signal actually. Continuously we are applying the two types of signal. For example, if I am going to apply the large sinusoidal signal, large means it is may vary from plus 5 volt to minus 5 volt. This type of signal we are applying. This is the signal, or this is the signal. This is the high frequency signal. Continuously we are applying this signal at this point in the place of what is VGS. So VGS is a variable. VGS is a variable, continuous variable from minus 5 to plus 5. A voice, everyone that, sorry, how you to response in 1 minute? Hello, hello. There is some problem. Yes, sorry, 1 minute. Voice is okay, audible sir. So why Ravi? Increase your volume. It's fine, everyone saying that fine. No, that is public view. Navneet, Panod have given the feedback. Ravi, please change your system. Okay then. Plus, this is the, okay, try to understand. This is a variable VGS, so we are applying from negative to positive. So when I am giving the negative, slowly it will increase from negative to positive, minus 5 to 0 and 0 to what? Plus 5. It will take time because it is a very slow. So first of all, during negative it will attract holes, then 0 it will repel the holes, after 0 up to threshold it will repel the holes, depletion layer will increase, and finally for the plus 5 it will attract the electron. So all the three will occur properly. Okay, that is clear everyone, any doubt? All the three mode. Because we are giving the sufficient time for accumulation and sufficient time for inversion. This is the case. After that it will start depletion, maximum depletion, and finally it reaches to, this is the case. This is the VT. So already I have given this is the accumulation, this is the depletion, this is the inversion, and this is called strong inversion. But in case of high frequency signal, it is negative, then it will reach to what? Positive, then again it will reach to what? Negative, very fast. So when it is very fast, so when the negative comes, hole will accumulate. Why? Because there are large number of holes are present, already present here. When large number of holes are present here, they will accumulate. Is there? It is clear? Why there is a large number of holes? Because it is a P-type. Large number of holes are present here, and when we are giving the negative charge, finally it will accumulate in this region. So there is no problem in the accumulation, and it is just like oxide capacitance. When we are giving the negative voltage, or when we are increasing the minus 5 to 0 and so on up to VT, it will repel the holes, depletion layer will form. But when we are increasing up to what positive voltage, it will not get the sufficient time because the frequency is very, very high. Again, suddenly it will reduce to minus negative. So at this point or at this point, what is the difference? We have sufficient time here, but here we are not having the sufficient time, and during that time, the electron, it should attract what? Electrons, but electrons are minority carriers. There is less number of electrons, and here electron, but it will take time for the diffusion. It will take time for generation, and that's why there is no proper inversion. Okay? So which part will not happen? Inversion will not happen in high frequency region. Any other student, any doubt? Vignesh, nod is clear. Practically that is the diagram. After that there is no change. It will reach to minimum and it will remain at minimum. This is for very high frequency, in the range of what? Megahertz. Right? Otherwise low frequency inversion occurs. This This is in the range of hertz. Now there are two ways. One is what in abundance, another one is what from minority carrier. But both abundance means what? It will take time. Now diffusion from higher concentration to lower concentration. It will take some time, but we are not giving sufficient time. Second, generation. Again, it will take time for generation. Both the procedure will take time. We are not giving the sufficient time. Okay. If suppose we want to, what is this? Ravi, sir, with our threshold voltage not construct MOSFET means? The language is not clear, Ravi. No. What? Now tell me everyone, it is a high frequency response or low frequency? That type of diagram they will give. Okay? So it is a high frequency response. High frequency, how to solve the question? Very, very simple. The figure shows the, what is the answer for this question, everyone? How many students solve this question? Answer, give the answer in the poll. Threshold voltage. Threshold voltage we can define after just the minimum value of the voltage after which the conduction will start. Okay. We are applying the VGS. Threshold is just like a 13 voltage. Okay, 73% student have given the A option. Now I will check. What Ravi that? Just it is a threshold voltage. Up to threshold voltage, it will repel almost. It will repel what? Electrons. And just after that, the conduction will start. Means conduction will start with what? Now it will start attracting the electrons, and that's why suddenly it will increase. In a Satter and Smith, there was one definition that at threshold voltage the conduction will start, but practically up to threshold there is no conduction, and just after the conduction suddenly the curve will change. So we can say knee voltage or cutting voltage just like a BJT. Okay, Ravi? More practical approach. We have to apply the more practical approach, and again I will give the more about the threshold voltage. Today we will discuss more about the threshold voltage. Okay. Now how to solve this question? Simply, figure shows the high frequency or metal oxide semiconductor having area is given. Assume that the permittivity of silicon is given and SiO2 is given. The gate oxide thickness. Gate oxide thickness in the MOS capacitor is, okay, we have to calculate the TOX. It is a formula based question. So what is the formula? Here the 7 picofarad is given. So what is the 7 picofarad, my dear? According to the graph, it is the COX dash. What is the COX dash? A into COX. Overall, normally we are giving the capacitor per unit area, but it is the capacitance is given. It is not a per unit area. It will become ACOX is given. So what is the, from the diagram, what is the ACOX 7 picofarad? So directly you can apply. Okay, directly you can apply this formula. ACOX 7 picofarad. 7 into 10 raised to power minus 12 farad. What is the area? Area is given as 1 into 10 raised to power minus 4. What is the COX? Epsilon naught x by TOX. That is 7 into 10 raised to power minus 12. Now what is the TOX? 1 into 10 raised to power minus 4 into epsilon naught x. What is epsilon naught x? Epsilon or epsilon naught. That is given as 3.5 into 10 raised to power minus 13 farad per centimeter. Okay, no problem. Upon 7 into 10 raised to power minus 12. This is the farad. Farad cancel. Now, right, area. What is the area? It is given in centimeter square. Area is given in centimeter square. That's why the answer will be in centimeter. So what is the answer? Now, this is very simple. This is the 0.5. And this will become minus 1. This will become minus 5. So we can say 5 into minus 6 centimeter. Yes, we can write. Tell me everyone. This is 0.5 into 10 raised to power minus 5 centimeter. Right. Now, convert it into what? Answer is given in nanometer. So what is in nanometer? When I am writing it 50, it is multiplied, it is divided by the 100. And 1 nanometer is equal to 10 to the power minus 9 centimeter and 10 to the power minus 7 centimeter. Sorry. That's why it will become 50 nanometer. Easy, guys? Formula based question directly. No doubt. Now, linked question. What is the answer for this one? I will not going to give you the more time, because it was the assignment. The figure shows the high frequency capacitance characteristics of a metal capacitor having an area of, same question, everything is same, maximum depletion layer width. Somewhat tricky question. Yes. 33% student have given the right answer. Priya Mohan, Ravi Chavli, Navneet. Okay. So these are the ranks. Okay. Now, a very tricky question. When we want to find the maximum depletion layer width, remember that. First of all, everyone, draw a rough diagram. You are not drawing on a rough diagram, so that you will get the idea that this is the case. Try to visualize the thing. Don't try to mug up. Right. That is the depletion layer increases maximum. Remember that concept, everyone? This is the depletion layer maximum. Maximum occur at which point? When we are providing VGS is equal to what? VT. Maximum. Right. When there is a maximum, there are the two capacitance. One is the oxide capacitance and one is the depletion capacitance. These two are in series. So what is the total capacitance? Now I am saying about the capacitance, not per unit area. The total capacitance is the series combination of the oxide capacitance and semiconductor capacitance. That is nothing but depletion capacitance. Okay. Now what is this? 1 by C equivalent is equal to 1 by COX plus 1 by CS. Now exactly at VGS is equal to VT. What about the depletion layer? Maximum. That is the threshold. This is called maximum depletion layer, or this is called depletion layer exactly at T for threshold. Okay. Now what is the at this point? What is the capacitance of this semiconductor material? This will become A epsilon S by what? HT. Okay guys, this is clear. And this is the minimum. This is the minimum capacitance. When this is minimum, this is also minimum. So what is the C equivalent minimum? C equivalent is the vector material. What it is maximum? There are the. Don't try to mug up. Trying on a rough diagram. First of all, everyone, draw a rough diagram. You are not drawing on a rough diagram, so that you will get the idea that this is the case. Try to visualize the thing. Don't try to mug up. Right. That is the depletion layer increases maximum. Remember that concept, everyone? This is the depletion layer maximum. Maximum occur at which point? When we are providing VGS is equal to what? VT. Maximum. Right. When there is a maximum, there are the two capacitance. One is the oxide capacitance and one is the depletion capacitance. These two are in series. So what is the total capacitance? Now I am saying about the capacitance, not per unit area. The total capacitance is the series combination of the oxide capacitance and semiconductor capacitance. That is nothing but depletion capacitance. Okay. Now what is this? 1 by C equivalent is equal to 1 by COX plus 1 by CS. Now exactly at VGS is equal to VT. What about the depletion layer? Maximum. That is the threshold. This is called maximum depletion layer, or this is called depletion layer exactly at T for threshold. Okay. Now what is the at this point? What is the capacitance of this semiconductor material? This will become A epsilon S by what? HT. Okay guys, this is clear. And this is the minimum. This is the minimum capacitance. When this is minimum, this is also minimum. So what is the C equivalent minimum? C equivalent minimum is nothing but 1 by COX plus 1 by CS minimum. So once you will get the CS minimum, you can find the HT, everyone, yes or no? When the depletion lift is maximum, capacitance because of the transition region or depletion region, that is called the capacitance inside the semiconductor. We can find the value of HT. Okay. Now what is the C minimum? C minimum from the diagram, everyone tell me what is the C minimum in the given C equivalent. Where is the C minimum? This is the C minimum. Exactly at what VT? 1 picofarad. What is the COX? This is nothing but COX, 7 picofarad COX dash. Because it is a complete, this is the COX dash, we can make it what COX dash. 1 picofarad. We have this. So you can find a C minimum, everyone. Yes. 1 picofarad, 1 by 7 plus 1 by CS minimum. Everyone from this find the 1 by CS minimum. What is the CS minimum? 1 minus 1 by 7 will become 6 by 7, or CS minimum will become 7 by 6. We can find. So from this you can find the CS minimum is equal to 7 by 6 picofarad. 7 by 6 picofarad. Okay, now once you will get the value, what is the CS minimum? A epsilon S upon HT, that is called maximum depletion rate, is equal to 7 by 6 picofarad minus 12. What is the area here? Area is given 1 into 10 to the power minus 4. Area will remain same. Epsilon S, semiconductor. What is the semiconductor epsilon S? Silicon. 1 into 10 to the power minus 12 upon HT is equal to 7 by 6 into 10 to the power minus 12. Please solve that. HT 6 by 7, right? It will become minus this 12 cancel, 10 to the power minus 4. What is the 6 by 7? 0.857 centimeter. To convert it into micrometer, answer is correct? Easy. So no need to mug up the formula. No need to mug up the formula. Already I have given these two capacitors are in series. So what is the series equivalent? This is important formula. This is an important formula. Directly we can find the capacitance, and from that we can find the maximum depletion layer. Anyone any doubt, then you can ask. This is a very very important question for GATE exam as well as engineering services and other competitive exams. Very conceptual question. No doubt. Next one. For last question on that same diagram. Consider the following statement about the CV characteristics plot. This is given, okay. This is the COX test. This is the C minimum. Everything we have calculated. The MOS capacitor has N-type substrate, okay. If the positive charges are introduced in the oxide, the CV plot will shift to the left. That is the point. I am not giving you the idea, but you can think about that. Logical question. Chale, participate in the poll. Now, in your short notes, everyone, try to draw the diagram actually. Draw 1 time, 2 times, 3 times, 5 times. Try to make all the diagram on your short notes. Then you will no need to then further revision, right? If suppose we are just simply read it like novel, then it will become very difficult. 63% students have given the right answer. Okay, Priya Mohan, Ravi Chandli, Navneet, Sriza, Nivita, then Monica. Okay then. Now, my dear students, first MOS capacitor has N type. No. Here the threshold voltage is positive. If the threshold voltage is positive, means what? It is an N channel, right? N channel means what is the body type? Body type is P type. That is the wrong. Alright. In the given C equivalent, where is the C minimum? This is the C minimum. Exactly at what Vicky? 1 picofarad. What is the COX? This is nothing but COX, 7 picofarad COX test. Because it is a complete, this is the COX test, we can make it what COX test. 1 picofarad. We have this, so you can find the C minimum, everyone? Yes. 1 picofarad, 1 by 7 plus 1 by CS minimum. Everyone from this find the 1 by CS minimum. What is the CS minimum? 1 minus 1 by 7 will become 6 by 7, or CS minimum will become 7 by 6. We can find. So from this you can find the CS minimum is equal to 7 by 6 picofarad. 7 by 6 picofarad. Okay, now once you will get the value, what is the CS minimum? A epsilon s upon ht, that is called maximum depletion rate, is equal to 7 by 6 picofarad minus 12. What is the area here? Area is given 1 into 10 to the power minus 4. Area will remain same. Epsilon s, semiconductor. What is the semiconductor epsilon s? Silicon. 1 into 10 to the power minus 12 upon ht is equal to 7 by 6 into 10 to the power minus 12. Please solve that. ht 6 by 7, right? It will become minus this 12 cancel, 10 to the power minus 4. What is the 6 by 7? 0.857 centimeter. To convert it into micrometer, which answer is correct? Easy. So no need to mug up the formula. No need to mug up the formula. Already I have given these two capacitors are in series. So what is the series equivalent? This is important formula. This is an important formula. Directly we can find the capacitance, and from that we can find the maximum depletion layer. Consider the following statement about the CV characteristics plot. This is given, okay. This is the COX test. This is the C minimum. Everything we have calculated. The MOS capacitor has N-type substrate, okay. If the positive charges are introduced in the oxide, the CV plot will shift to the left. That is the point. I am not giving you the idea, but you can think about that. Logical question. Chale, participate in the poll. in your short notes, everyone, try to draw the diagram actually. Draw 1 time, 2 times, 3 times, 5 times. Try to make all the diagram on your short notes, then you will no need to then further revision, right? If suppose we are just simply read it like novel, then it will become very difficult. 63% students have given the right answer. Okay, Priya Mohan, Ravi Chavli, Navneet, Sreza, Nivita, then Bonita. Okay. Now, my dear students, the first MOS capacitor has N type. No. Here the threshold voltage is positive. If the threshold voltage is positive, means what? It is an N channel, right? N channel means what is the body type? Body type is P type. That is the wrong. Already I have given. This is the diagram. Body type is N type. Right? Any doubt? N positive. Body type is P type. Because the threshold voltage is positive. Right. Threshold voltage is positive, and that's why the body type is P type and channel is N channel. Channel is no doubt N channel. So this is not the correct answer. This is not the correct answer. Now you have to choose from what? C and D. Both S1 and S2 are false. So yes, that is we have to choose from these two. So you can give the just guessing which answer is correct. So 50% probability answer may be right or answer may be wrong. How many students given the answer like that? Yes, please tell me. Okay, no problem. Now, suppose if the positive charges are introduced in the oxide, then what will happen? Actually, if I am introducing the positive charge, today I will give you the exact formula, but very common sense, If I am introducing some positive charge in the oxide, what about the threshold voltage? Actually, we want to attract the electron. So initially we are considering that there is no charge trapped inside the oxide. Yes, I have given you the assumption that no charge is trapped in the interface, no charge is trapped inside the oxide, and we are applying the voltage here. And like this is the 1 volt, it is a threshold voltage. After 1 volt, it will start attracting the electron. Okay. But suppose if we are having the positive oxide here, so definitely it will help to attract the holes, electrons, yes or no? Yes, it will help us because the positive will attract the negative. So when the positive will attract the negative, or it has some negative positive charge inside the oxide, definitely what about the VT? VT will decrease. Threshold voltage will decrease. Suppose 1 volt is required to attract the 1000 electrons. Now, if suppose already there are some holes, 100 positive charge are here, then this 100 positive charge already attract the 100 electron, then only 0.9 volt is required to attract remaining 900 electrons. This example is clear? This is an impurity inside the oxide, right? During manufacturing SiO2, some impurity will be there. It may be positive ions, negative ions. Normally positive ions are present inside the oxide. Okay. Today we will discuss all these things. So which answer? If the positive charges are introduced in the oxide, the CV plot will shift left. If the threshold voltage decreases, then it will shift left. This is the case. Shift left. Okay. Now. Okay. So these are the 3 questions. So in the previous class, today we are going to discuss what is the accumulation and what is the depletion and what is the inversion and what is the effect on the Fermi level. Right. Accumulation means there is an accumulation of the holes in this area. This is called channel length. This is the channel. Depletion means depletion layer increases here. And inversion means it will attract electron. Here we are giving positive. Here it is increased up to what? Threshold. Here we are giving negative. These are the cases: accumulation, depletion, inversion. This is the P type. Let I am assuming that P type is the N positive and positive P type substrate. P type. Now remember that this is a semiconductor material. Up to this point it is a semiconductor. Okay, please focus on the channel length only. This is the channel. It is a semiconductor. It is SiO2 layer. Here we are having the metal. Here it is a gate terminal. Okay. Please focus on the highlighted portion only. Now I am going to change the orientation of this highlighted portion. So this is the metal, then SiO2 layer, and then what? Semiconductor. The width of the semiconductor is high as compared to what? SiO2 layer. So when I am in a vertical direction, this is the thickness of the SiO2 layer, POX. This is the thickness of the that value. Okay. So different types of concept here. Now I am going to use here. Now try to understand. First of all, tell me when I am applying the negative voltage between them, during accumulation, what will be the direction of the electric field? Watch this diagram. Above plate become negative. Below there is accumulation of the holes. What is the direction of the electric field? Always remember the direction of the electric field will be from positive to negative. This is the positive to negative. So this is the p-type. Hole is accumulated here, and the direction is from positive to negative in the opposite direction. Now, this is a very accumulation layer of holes. A parallel plate capacitor. This is just like a parallel plate capacitor, showing the electric field and conductor charges. In a B diagram, a corresponding MOS capacitor with negative gate bias. This is a negative gate bias, showing that the electric field and the charges flow. The MOS capacitor with an accumulation layer of the holes. So everything that simply we are showing the electric field, then here the charge it will attract the holes, and then finally there is accumulation of the holes. This is the case. This is we can directly watching this diagram we can say it is what accumulation. Sometimes that is the diagram. And this is from the standard textbook, that is Neiman. Okay. The next diagram, I think that is clear to you everyone. What should be the polarity? Above negative, below positive. That direction is from positive to negative. Very simple concept. Now, this is again when I am saying that when I am applying the positive voltage, I am not applying the very high positive voltage, just like the MOS capacitor with a moderate positive gate voltage. Read this point. Moderate positive gate bias. Showing the electric field charge flow. What is the electric field charge? This is the plus, that is the minus. First of all, it will repel the holes. This is the repel direction of the holes. It will repel the holes. When it will repel the holes, depletion layer will increase. Induced space charge region. Yes, in every case there will. This is called. That's why it is called field effect transistor. That's what is called field effect transistor. That someone will force the hole to move away now. Someone will force or attract. The force will attract or repel the charge carrier. So when we are giving the positive, first of all, it will repel the holes. So that is what is the direction. Watch the direction carefully. Repelling the holes. Depletion layer increases. Induced space charge. Induced space charge region. Okay. Third case. Now what is the formula? Third case is what? Inversion. Inversion, I will explain inversion. You have an idea about that. Already I have given the diagram. This is the inversion. In inversion, this is plus, and in below minus. So what is the direction of the electric field? Downward. Plus 2, minus. Inversion, plus 2, minus. Okay. Now, according to Fermi level concept, if I am having the p-type material, where will be the Fermi level lie? Near to what? Valence band. This is the Fermi level. This is EFI, intrinsic Fermi level. This is the conduction band, valence band, and this is EFP, EV. And this gap is nothing but when we are calculating in what? This is the KT log of Na by Ni. KT log of Na by Ni. Remember that this is nothing but Q. That is called work function. I will introduce the new function that is represented by phi, and that is given by Q times of potential. What is the potential? The potential is KT by Q log of Na by Ni. This cancel and we are getting the KT log of Na by Ni. So what is the work function actually? The work function is nothing but KT by Q log of Na by Ni. It is just a difference. We are in a first chapter we are saying that what is the when we are calculating the difference in terms of what volt. So it is in the electron volt, and we want the shift in terms of volt. Then we are directly saying that KT by Q log of Na by Ni, that is the result in what volt. So this is a simple representation phi. Right? In a different textbook, suppose in Neiman they will use the phi, in other textbook they will use the VBI, and so on. So this is the case. And suppose it is converted into what? It is converted into N-type. Then where will be the Fermi level everyone? For N-type semiconductor. Initially the Fermi level was here. This is the gap. And now, when it is converted to N-type, now the Fermi level will be here. And this gap, for strong inversion, this gap should be KT log of Na by Ni. Right, upward. So what is the gap from initial Fermi level to final Fermi level? Initial Fermi level to final Fermi level, the gap is 2 times of KT log of Na by Ni. 2 times. Not Nd. Where is the Nd? Where is the Nd? We are giving the Nd. Everyone tell me. Tell me, we are giving the Nd. We are doping with the Nd. Anyone? No. We are repelling the holes. We are simply repelling the holes. So when we can say that is converted into inversion layer. Okay. So what is the concept? when we can say there is strong inversion occur, initially it is a p-type, then what is the position of the Fermi level? Below the EFI by how much amount? Kt log of Na by Ni. So when the inversion occur, what about the Fermi level? Above the Fermi level. By what value? By the same value, Kt log of Na by Ni. Then we can say strong inversion occur. That is the concept. Okay? This point is clear. We are not giving the ND there. Okay, that's why this is a very, very important concept, that numerical. Directly they will ask you the numerical. Okay. Automatically it is converting into N. Yes. Because that is repel the holes, it will attract the electrons. The Fermi level will shift. And that's, we can say, now it is converted into what N. So this much voltage is required. Suppose it is in what? Electron volt energy. So when we want to convert it into voltage, what will be the voltage everyone? 2 kT by Q log of Na by Ni. For strong inversion, first of all, this much voltage is required. But at the same time, if suppose we are adding positive charge to oxide, then what about this requirement? It will reduce or it will increase, everyone? Initially we are considering there is no charge trapped inside the oxide. If suppose there is a positive charge inside the oxide, definitely this requirement will what? Reduce. This requirement of voltage is reduced. Again there is some charge trapped in interface of the semiconductor and oxide. Again that will reduce. So finally we will get the formula. Finally we will get the formula for the threshold voltage. Okay? This point is clear? Before that, first of all get the idea about these three diagrams. Right? Okay. So one by one I want to explain you. This is a very, very important diagrams. For example, this is the semiconductor. This is a very conceptual diagram to please. This is the oxide layer. And this is the metal plate. And this is the metal plate. We are not adding there. Contamination is always there. We don't want. The weakness, we are not adding. Sometimes it will support or sometimes it will not very dangerous also. Okay? Everywhere impurity is present. And that's why the IC fabrication is not so easy task. Okay? Now we are going to start some factories. NaIon will present backside to that, no problem. Na is a, what about the NaIons? NaIons are what immobile charge carriers, and that's why they will not help in the conduction. And okay, please watch this diagram and you will get the idea. It is a p-type substrate. So I am giving you the level. First of all, this is a metal, SiO2, and this is the silicon. Silicon is p-type. I am directly drawing the energy band diagram. The energy band diagram, according to energy band diagram, this is the Fermi level, EFI. Now, this is conduction band, this is valence band, right? This is the Fermi level actually. FP because it is a p-type substrate. There is no IC. I am not going to apply any voltage here. This is a very simple case. This is the energy band diagram. First of all, when I always remember the under equilibrium, the Fermi level will maintain the same because we want to represent the diagram. We want to show the diagram. It is a tentative diagram, so we want to show the energy band diagram. So EFP will remain at this point. Okay, there will be no change. Everyone, tell me when I am increasing the Na. When I am increasing the Na means, or when I am increasing the concentration of holes, the gap between EV and EFI will decrease. Yes? When we are increasing the concentration of holes, the gap between EV and EFI decrease. The gap between EFP will decrease. EV and EFP will decrease. Second thing, the gap between EC and EFP increase. Yes, this is the case. Gap between EFI and EFP increase. And this gap will decrease. So when I want to show EFI and EFP increase, and this gap will decrease. So when I want to show the accumulation in the diagram, so actually this is a case when there is no biasing. But when I am giving the negative voltage here, then what will happen? At the far end, there will be the no effect. But finally, the holes will collected near to a junction, near to the interface of the semiconductor and SiO2 layer. Yes, so here the holes will accumulate. When there is an accumulation of the holes, the Fermi level at this end will bend. The Fermi level will bend means this is moving. This is the EV. It is moving near toward EFP. The gap between EV and EFP decreases. It will not change. It is under equilibrium. It will remain same. This will bend away. EFI move away from EFP. EC move away from what? EFP. So simply in exam they will give you this diagram, and by watching this, tell me it is a accumulation, inversion or depletion? Everyone. Just the bending of the energy level. The bending of the energy level means EV is moving towards what? EFP. EFI is moving away from the EFP. EC is moving away from the EFP. Means we are making it more P-type. If it is more P-type means what? It is a accumulation. Simple logic. Accumulation. Okay? This is clear? This diagram is clear? Okay, very simple. So this is the 1 minute. Where is the diagram? Yes. Tell me, watch this band, and another thing, if nothing is given, tell me it is a P-type or N-type. Suppose it is not mentioned here. It is a P-type or N-type. That under equilibrium, that is the reference. Already in a Fermi level, I have shown you that we are taking the actual Fermi level as a reference. So when we are taking it as a reference, so what about the other? The conduction, lower EC will move away, EFI will move away, EV will move towards what? EFP, and that is the case. Okay? That is the representation actually. It is a P-type. Directly from the bulk of the semiconductor, from here, always watch. EFP is nearly, or Fermi level is nearly near to what? EV, and that's why it is a P-type material. Substrate is P-type, means channel is what? N channel. So this type of objective they may ask. They will give you the diagram, and simply we have to ask. Where is the bending in the EFP? I have given the bending weakness in EFP. I have given the bending in what? EC, bending in EFI, bending in what? EV. There is no bending in what? EFP. Okay? Always remember we have to check with respect to what? EF. So watch this diagram. That is the diagram from the standard textbook. Already I have given the name. This diagram is clear. Accumulation layer of the holes. That's why it is bend. Okay. Now, in the second case, when we are applying the moderate positive voltage, moderate. When we are giving the moderate positive voltage, it will repel the hole. When it will repel the hole, there is a deficiency of the holes. When there is a deficiency of the hole, what will happen? EV will move away from the EF. EFI will move towards what? EF. EC will move towards what? EF. Right? And tell me, if it is initially P-type and we want to make it what? N-type, so when it is, there is a journey from P-type to N-type, then in between it will become what? Intrinsic type, yes or no? Journey from P to N-type means first of all, P to what? Intrinsic, then intrinsic to what? N-type, yes? That watch this diagram. When we are giving the positive voltage, what will happen? First of all, EFI coincide with the EF. It is visible here. EFI coincide with the EF. EV move away from the EF. EC move towards EC. EC move towards EF. Okay. It is just a inversion. Depletion layer increases. There is no inversion, only depletion. Only depletion. Because we are applying a moderate positive gate bias. Okay. Finally, when I am giving the more positive voltage, then what will happen? Watch this diagram. Very, very important one. Right. Now, it is a P-type material. What about the EV? EV move away from the EF. Which is near to the EF? Conduction. EC is near to what? EF. EC is near to EF. Because in N-type, always remember, in N-type, what is the sequence? First of all, EC, then EF, then EFI, then what? EV. First of all, EC, this is the EC, then EF, this is the EF, then EFI, this is the EFI, and then what? EV, this is the EV. It is visible, everyone? There is a banding, very large banding, and this is called what? Inversion. This is called inversion when the Fermi level reaches near to what? Conduction band. Okay, so this you can compare with this N-type. And here we are applying a large positive voltage. So what will be the question? Actually, I want to give you the idea about the questions. They will give you that, they will not mention this. Watch this diagram, and they will not mention this. From the bulk, you can say it is a P-type. From this EV, EF is near to EV, that's why it is a P-type material. Exactly at the interface, watch, there is an inversion because now the EF is near to what? EC, and that's why we can say it is an inversion. Material is P-type. What is the voltage applied at the gate terminal for inversion? Definitely it is a large positive gate voltage. That type of objective question. Any doubt? Now I am giving all the three diagrams in one slide. Accumulation, depletion, inversion. Every student, first of all, you have to draw the diagram like this on your rough page. Yes or no? If suppose you are just reading like a novel, then it will become very difficult. It is a reading like a novel means what? You are not going to get the idea. Do you want to clear the exam? Yes or no? Everyone, do you want to clear the exam? Yes. Then you have to, with the help of, with self-study only, I have cleared multiple times. No, it is not just I'm giving you a study or every time you are saying like that. Okay, I have the idea you have got the rank and so on, so on. My dear, at that time, no net and no facility. I have gone through all the textbooks and so on. No, I am not a legend. All those things. Just I am giving you a simple thing here. But then, what happened? At that time, mobiles are not available. Right? So if I am giving you a simple thing here. How many, everyone tell me, from last class and this class, how many times I have drawn this box? How many times I have drawn this box? Tell me. Minimum 50 times. Right? Every time. Like one student have already given the 50 times. Right? Now, when we are writing continuously, then what will happen? If suppose we are writing anything for minimum 10 to 11 times, then it will set in our this mind. Right? And then it is a very rare chance that we will forget that all these things. Okay, and that's why writing practice is important. I have qualified multiple times because I am in the field of teaching. Every time I am explaining, I am drawing each and every diagram. Note down, all the PDFs are available. Okay, watch my slides, all the PDFs are available. But again I am drawing. Why? To explain it very clearly. All the PDFs are available. Okay. In subconscious mind, we can say. Now, finally, this is the inversion. Duration layer electron. Now watch all the three diagrams, you can compare here. You can compare these three diagrams. This is a p-type or n-type. What is the channel? Everyone tell me. What is the channel here? No, that is the given now. What is the channel? Array, always. Body is what? N-type. EF. EF is near to what EC? It is the body is N-type. So what is the channel? Channel is NP channel. Okay. So when we are giving the positive, this is called accumulation. This is called what? Accumulation. It will accumulate the electron. And that's why downward. The distance between EC and EF will reduce. Decreases. Second. During depletion, distance between EC and EF increases. This is visible. This distance increases upward. On it just double. And distance between EV and EF reduces. EC and EF increases. So this is called inversion. Inversion means there is a collection of holes, not electrons. I think that is clear. This type of diagram is objective. They will not going to ask other question. Simple by diagram. What is this? We can say it is N-type, means P channel, inversion, accumulation, and so on. Okay. What is the doubt here? Navneet. Sir, in the inversion mode, electron is getting collected near oxide layer, but where will be the negative ions? Na ion will be backside. Okay. Navneet is asking one question. I am trying to give the answer. Always remember, we are having the ions here. What is the size of the ions? Very large. Okay, Navneet? We can't move the ions. But here, when the electrons are attracted, these are come to near to the surface of the semiconductor, SiO2 layer. And it will increase the conductivity of the channel. They will present, they will remain there, negative ions. Depletion layer will remain there, okay? No problem. Many more things here to discuss all these things. First of all, 1 minute. Up to this point, no doubt. Up to this point, no doubt. Okay. Now, there are three modes in mathematical, or when we are giving the equivalent model, high frequency model. In analog, we are using this small signal model. This is the common source, this is the drain. Here we are connecting the VGS. Okay. So this is the small signal model at low frequency. At low frequency. But when we are considering why at low frequency? Because all the capacitance, because of the impedance, because of the capacitor is given by 1 by 2 by Fc. Since all the internal capacitance are normally in the range of picofarad, and the frequencies it is in the range of, suppose it is in the range of kilohertz or hertz. But what about the impedance? This is very, very large. And that's why all internal capacitance act as open circuit. all internal capacitance act as open circuit. Okay, but when we are increasing the frequency, then what will happen? The impedance start decreasing. Now we have to consider all these impedance at a high frequency. What is the change in the high frequency model? High frequency analysis of BJT, we have to consider the capacitor in between these two. We have to consider the capacitor here. We have to consider the capacitor here. Yes or no? This is called what? CGD. This is called CGS, CGDS, and we have to apply the Miller's theorem. Then we are solving this question, right? No. When we are talking about the diffusion or transition, that is the part of what BJT. We are saying that there is a capacitance between what gate and drain. There is a capacitance between what gate and source. So what are the values in EDC? Now I am going to explain you. Okay, guys? This is clear? What is the CGD or CGS? So this type of capacitance, mathematical models. What about the values? This type of questions they may ask. Okay. One by one. First of all, we are having the reasons. First is the triode region, saturation region, and cutoff. Yes, I am talking about the internal capacitance. The triode, saturation, and cutoff. You will get the idea. Okay, no problem. First, so I am explaining the triode region first of all. So after 10 minutes, you can ask any doubts. Right. In a triode region, channel is uniform. Right? Very small radius is not large. Channel is uniform. When the channel is outing, well, it is just near to the surface. Only I am going to tell you about that. This inversion is there outside there. On one side we are giving the positive charge, on the other side we are giving negative charge. No tapered shape, channel is uniform. When the channel is uniform and when we are calculating the capacitor between these things, positive and negative, then static is nothing outside capacitance COX. What is the COX? A COX. What is the A? W into L. W is the width, L is the inlet. COX ln naught S by TX. That is the formula. Okay. Now in mathematical model, when we are in the model, just like it is in the model, then this capacitance is between what drain and what source, equally between the drain and the source. So we are dividing it into two parts. We are dividing it into two parts. One is given, so the gate is given. So half is given to gate and drain and half is given to gate and source. Therefore, triode region, the CGS will come COX by 2. That is nothing but 2TX. Right. And half is given to gate and drain. Okay, so half is given to what? Half is given to gate and source and half is given to gate and drain. So remember, very simple, right? So this is the during triode region. Now I am going to tell you the saturation and now the final can ask question. Second one, in saturation, channel is backward shape. When the channel is of backward shape, in saturation region there is a bit of channel. It is not uniform. Radius is large. Now when we are calculating the capacitance, actually what the capacitance is, the capacitance is given by 2 by 3 WL COX. Where the COX is nothing but epsilon naught S by DOX. This is the 3.9 epsilon naught by DOX. Same. What the capacitance is WL into COX. This is the WL into COX. But it will become 2 by 3 WL COX. Why it will become 2 by 3? Because of the capacity. No need to get the formula, remember that. 2 by 3 WL COX. That is actual capacity. It is calculated on model. We have two choices. Half should be given to what gate and drain, half should be given to what source and gate. But when the channel is pinched off, the channel is pinched off near drain. Right? That's why capacitance is nearly equal to the complete capacitance. Complete capacitance is given to between gate and source terminal. That's why the CGS. CGS will become 2 by 3 WL COX. And what is the CT? Is given to gate and drain, and that's why it is 0. And what is the between gate and body? Again it is 0. Gate and body, it is what? This is also in a gate body terminal, it is 0. Okay? Right. Third case, the cutoff. In a cutoff, there is no channel. We are giving normally negative value here. For cutoff, we are providing a negative value so that it will remain cutoff. So normally all are collected here. There is no current. So this is called cutoff. Again, here we are having the negative charge. Here we are having the positive charge, just like accumulation. So what is the capacitance, everyone? Again, the oxide capacitance. So what is the oxide capacitance? A into COX. What is the A? WL into COX. What is the COX? Epsilon naught x by TOX. Now, if it is in cutoff, there is no model. Then in the cutoff, this complete capacitance is given to what? Gate body. Gate body. COX test. WLCOX. So what is the CGD? 0. What is the CGS? 0. Nothing is given to CGD and CGS. So there are three reasons. Triode reason, when the channel is uniform. Saturation reason, when the channel is tapered. Pinch off point, and then third is what? Cutoff. So we are distributing these three capacitors according to the in models. When we are giving a small signal model, already I have given you the model. What is the model here? CGD, CGS, or between what? Gate and body terminal. Here we are having the body terminal. We can connect it between the gate and body terminal. But gate and body terminal normally we are using for higher system. So normally we are not getting the question on gate and body terminal. But we are using this model in analog. Yes or no? High frequency analysis. But in a high frequency analysis in analog, they are not going to ask you what is the value of the CGS and what is the value of the CGD. In a particular numerical, they will give you the value of the CGA and CGD, and they will ask, find the gain bandwidth product, what about the bandwidth, and this type of questions. Yes, CGS, CGD, CDS, both are 0 in case of cutoff. In case of cutoff. And complete capacitance is given to what body? Right. No. We are not considering this. Let's say suppose we are entering into that the pinch of voltage is moving. No. Not required. During this, we are neglecting the channel length modulation. Okay, tell me everyone, we are doing the BTEC or PhD? Tell me. I am having limited time. 4 hours, 2 classes. Yesterday I have 1 class and today I have 1 class. In 4 hours I have to cover each and everything. Okay? Complete Niemann, complete Saturn speed, complete what? Niemann algebra. 4 hours. Is it possible? Second thing. Now we have one other class, but that is the problem. We have to discuss number of problems also. Right? No problem, Vignesh, you are asking, but just I am giving you the practical approach. Right? Suppose we are getting so much knowledge, but during competitive exams, we have to recall what? Only one subject or total 12 subjects? In GATE, we have to recall what? How many subjects? 10 subjects, for example. Maths, FT, or communication, EMFT, network, digital, or what other subjects, right? EDC, analog, right? These are the signal and system. So total 10 subjects. And for engineering services, everyone tell me. Advanced electronics, advanced communication, computer organization and architecture, material, measurement, machine. 6 extra subject. 10 plus 6, 16. Okay. And in every time there is some extra syllabus in every subject. Almost 18 subject. When we are comparing with the GATE, 18 subject. But depth knowledge is not required for pre-exam. Vast knowledge is required. 18 subject. Plus what? General studies. In general studies, we have only maths and FT common. Otherwise, environmental issues, lump sum, and so on. Right? No, it is not tough. It is a mind game actually. If it is a mind game, how it is a mind game? Simply, my dear, watch the last year toppers rank. We have to get only 60% marks to qualify what to get the top rank. Engineering services fee. So we have to focus on the 60% portion, means we can left what? Remaining 40%. Are you getting my point, everyone? And that is the trick to crack what engineering services. But normally students are focusing on what? This 40%. When they are focusing on the 40%, they can forget the remaining 60%. And it is very difficult to retain the very depth concept. Yes or no? How is it possible to get the command over the subject everywhere and on every point? It is possible to get the command within 60 hours or within 80 hours. Not possible. Practically not possible. To simply focus on the 60% for if you want to crack the engineering services exam. I am not talking about the GATE exam. Focus on the 60%. If suppose some subject is tough, you are not comfortable with that, leave it. Right? Some important derivations are there. No need to derive each and everything. Try to understand the concept. Because they will ask statement-wise question which statements are right or wrong, then we have to give the answer. But out of 300 marks, if suppose we are able to get the 220 or 230, more than sufficient, then we can drop 70 marks. Everyone try to get the 300 out of 300. Not possible. Go through the cutoff, everyone. Go through the, not cutoff, toppers marks. Last 5 years, toppers marks. You will get that. UPS is the very less, syllabus is very less, the competition is very high. Do smart work, not merely what hard work. Okay. And some students are 1 or 2, they are from what other planet, like what Mars and something else. Some are aliens. Don't worry about those aliens. Yeah, they have the command over each and everything, right? They have the command over all the subjects. English is very good. Hindi is also very good. Telugu is also very good. Everything. They have the command over the 5 subjects, 5 languages. They have the command over all the subjects. They are aliens. They are not from this world. They are from the other planet. So okay, no issue. Right? So leave them. So we can't compare with them. We only 0.000000001%. Rare cases. Okay, no problem. We are not extraordinary. We are normal. Normal students are doing the extra thing. They will become scientists. Okay. You can't become an idiot, right? Okay. Try to understand. With normal approach, we can find each and everything. Don't worry. This is clear? Now, I am going to give you a very important concept now. What is the overlap capacitance? I think these three things are clear. First of all, triode region. Second, this is a triode. Then second is what saturation, and then it is what cutoff. Now, what is the overlap capacitance? There is another important topic, overlap capacitance. What is this? This is a very important one. Overlap means, watch the diagram carefully. Right. When we are making this semiconductor, first of all, this is the N positive. This is the N positive. Actually, we want to deposit the SiO2 layer just here, just above the channel end. This would be the SiO2 layer. Okay? And then what is the length of the channel? L. This is the length of the channel is L. And what is the width? W. Okay. Right, watch this. This is the actually we want. This length is W. This is what SiO2 layer. The SiO2 layer L, so what is the area? This is the W. So what is the actual area? WL. And the capacitance per unit area is epsilon naught times by TOX. We are calculating. But what is the practical problem? There is a overlapping. Overlapping means because of the manufacturing process, it will diffuse up to this point. There is a overlapping of the semiconductor. Here we are having the overlapping. Because of this overlapping, actually the semiconductor will reach up to this point. Everyone, that is clear to you? Yes. This is extra. Here that is extra. It is above and positive. So when we are watching, this length is called overlap length. This is the overlapping here. This is del. This overlap length is called del L, or sometimes it is called del. Overlap length. On the both the side we have del L. So overlap length. What is the overlap area actually? This is the area. The overlap area will become del. What is the del? Into W. Now, what is the overlap capacitance will become on one side overlap capacitance. Overlap capacitance COV will become area into oxide capacitance per unit area. This will become del W COX. COX is this one. Now, sometimes they will ask what is the value of the overlap capacitance. The overlap capacitance on the source side, overlap capacitance on the drain side, right? Everywhere there is overlapping, and because of this overlapping, this is the COV. Okay? Any doubt? Now we are having the overlap capacitance on the left side, on the source side, on the right side, that is on the drain side. So here we are not considering it. Here we are not considering. Here we are not considering. Here we are not considering. Now there is a problem about overlap capacitance. Then, in every case, we have to add this with what? CGS and CGD, right? So practically, we have to add all this to what? CGS plus COV and CGD plus COV. Okay, guys? Because it is on both the sides. Towards gate side, towards drain side, there is a overlapping. So that is the practical problem during manufacturing of the or fabrication of the IC integrated circuit. So in a particular numerical, they will provide you the overlap length. They will ask you find the overlap capacitance and what is the overall capacitance in mathematical model. Then CGS plus COV. For example, if you are asking about the triode region, that is the CGS, that is the CGD plus what? Plus what? COV. We have to add COV here. We have to add COV here. If it is in saturation mode, what is the CGS? 2/3 WL COX plus COV. What is the CGD? 0 plus COV. What is the CGB? No need to add here. In a cutoff, this is 0. So CGD 0 plus COV, CGS 0 plus COV. No need to add in the body capacitance. Okay? So in every case, we have to add this overlap capacitance to CGD and CGS. So overlapping means what? When we are some area N positive, there is a overlapping of the oxide. Actually, we want to deposit the oxide just above the channel length. But because of IC fabrication problem, there is some overlapping. The oxide layer will come above the N positive source and N positive drain. Okay? And this is called overlap length. It is overlap, it is the front, we are watching from the front, but it is up to depth, it is up to what W. So what is the area, everyone tell me, what is the area, overlap area? This is the actual area. So what is the del A? What is the del A? A is WL. So what is this area? Del L into W. Del L into W. I think this is clear. The diagram, I am not perfect with the diagram, but I think that diagram is clear. Okay? in exam they will give you the diagram. In a GATE exam, this was the question. Try to solve this type of questions. Okay, tomorrow I will we will solve some questions on that. Remember that. It is very easy. Very easy. You can directly use the formula. Directly you will get the answer. Right? Okay. Next thing. Any doubt here? Energy band diagram of the MOS capacitor. This CGD small signal model. That is the triode saturation and cutoff. No. No. And now I am going to explain you that each and everything about that because it is a now I want to give you the idea about this formula. This is the formula for threshold voltage. What is the phi ms qi qd plus what 2 phi f. This is the total formula for the threshold voltage, and we have number of questions on this formula. First of all, these all are the basics. Read all these points first of all. I think okay, it is over. Now read this point. In the MOS capacitor structure that we have just considered, we assume the p-type semiconductor substrate. The same type of energy band diagram can be constructed for a MOS capacitor with n-type semiconductor substrate. Already I have given you the diagram. Figure shows the MOS capacitor structure with positive voltage applied to the top gate terminal. A positive charge exists on the top gate and electric field is induced with the direction shown in the figure. An accumulation layer of electrons will be induced in the n-type substrate. This is about what? P-type, n-type substrate. This is the theory about the n-type substrate, means p-channel. This is P channel. When the electron is collected, that is called accumulation. Then the depletion level increases, and finally holes will come. That is called universal. The case when the negative voltage is applied to the top gate, positive space charge region is induced in the region in the situation. This is the case, right? P channel, n-type substrate. This is about this diagram. Bending downwards and upwards. No. Bending downwards and upwards because of that. That is we are finding the energy band. Relatively, we are finding out that Fermi level means what? Fermi level is a probability distribution function. What is the probability of finding an electron at a particular energy level? That is the case, na? That was the case. Okay, guys. And when we are watching this diagram, that gives you the insight that whether it is accumulation mode or depletion mode or what, inversion mode. Okay. So with this diagram, we are finding the values. This is whether it is a p channel or n channel. We have discussed. Then this is the capacitance. Now, depletion layer thickness. First of all, exactly at threshold, we are having the highest depletion layer thickness. Everyone. Yes or no? Exactly at the threshold, we are having the highest depletion layer thickness. What is the depletion layer thickness at the threshold? VGS, when we are putting the VGS is equal to VT, already I have given, inside the semiconductor, the depletion layer will reach to its maximum, and what is the maximum? That is given by the HT. HT means the depletion layer at threshold. This is the maximum. After that, inversion will start. Now, we may calculate the width of the induced space charge region adjacent to the oxide semiconductor interface. Figure shows the space charge region in a p-type semiconductor substrate. The potential phi Fp, what potential is required? Actually, this is represented as that phi and something. This is nothing but a voltage. There is a difference between the EFI and EF, and is given by Vt log of Na by Ni. When there is a depletion layer, when we are just removing all the holes, then it just become what? It will just become like intrinsic semiconductor. Then we can say it is a complete converted into complete depletion layer. Now I want to explain this. This is the metal. This is the semiconductor. Initially it is p-type. Now we have some important formula. Everyone please focus on the one. This is the EFI. This is the actual Fermi level. This is the conduction band. This is the valence band. And this is the p-type substrate. It is actually an N channel. This is the SiO2 layer, and this is the metal, and this is the gate terminal. Now, how much voltage is applied here at gate terminal so that it is completely converted into depletion layer? When it is completely converted into depletion layer, means just we are removing the holes from this area. When we are removing the holes from this area, it is almost like what? Intrinsic semiconductor. Intrinsic semiconductor means we want to bend it up to what? EFI. We want to, well, this will move away from that. This will move away from that. Towards what? This EFI. EFI will become EFP. Then we can say it is almost converted into what? Intrinsic time. So what is this? Everyone tell me, in terms of voltage, what is this gap? In terms of energy, we have the idea that KT log of Na by Ni. But when we want to convert it into terms of voltage, it should be divided by what? Q. What is this? In terms of voltage, this is called KT by Q, log of Na by Ni. And that is nothing but Vt log of Na by Ni. When we are giving this much voltage at this point, that is completely converted into depletion layer. That is completely converted into depletion layer. Exactly at this one. Okay. Second thing, that is a Vt is equal to T by 11,600 volt. And remember everyone, Vt, what is the Vt? 0.026 volt at 27 degrees centigrade and 0.025 volt at 25 degree centigrade. Okay. Next thing. Now, when the inversion is required, we have to reduce. First of all, this will reach up to this point, and then we'll reach just, we want to convert it into what? N time. Then already I have given what is the energy is required, just double that of that. So for inversion, what is the voltage is required? 2 times of that. So it will become 2 times of Vt log of Na by Ni. Initially I have explained this. Any doubt? Initially I have explained this. Initially this gap was EF. Now we have to make this gap 2 EFP. This is the why we are multiplying it with what E, that is converted into what? Energy. When I am explaining it what just like a 5 FP, it is just a voltage, remember that. When it is multiplied with the Q or E, then it is what? In energy, that is called electron volt. This is the gap is required what? 2 times of is required. Okay, 2 times of that. Meaning, or in energy, it is 2 times of KT log of Na by Ni is required. When we are giving this much energy, it is converted from P type to N type material. This is already, in that case, the depletion layer is at its maximum, that is called threshold level depletion layer. Okay. Now, watch this. What is the formula for the depletion layer? So we have derived in case of semiconductor or in case of diode. What is the depletion layer capacitance? Depletion layer increases where the concentration is less. Here the depletion layer is negligible. This is the P type. Depletion layer increases inside the P type. What was the formula for depletion layer? At junction potential Vj, it is given by Qn upon 2 epsilon s into what? W square. This was the formula, everyone. Here it is increased s into what? W square. This was the formula, everyone. Here it is increases on the P side, and that's why in place of N we are using Na.